The neutral conductor should be grounded at the first point of disconnect. This location is generally the main electrical panel. Floating the neutral at subpanels is permissible, but not mandatory according to code. Grounding the neutral at the current transformer, or CT, is generally unnecessary and potentially dangerous. This practice introduces the possibility of a ground loop. Ground loops can negatively impact the electrical system's operation. The recommended approach involves grounding the neutral at the initial disconnect point and then allowing the neutral to float at any downstream subpanels. This configuration offers optimal protection against electrical hazards and ensures proper electrical system function. Let's delve deeper into why this is the case. When we talk about grounding, we're really discussing creating a low impedance path for fault current to return to the source. This path is critical for the operation of overcurrent protection devices like circuit breakers or fuses. When a fault occurs, such as a live wire contacting a grounded surface, a large current flows through this path, tripping the breaker or blowing the fuse, thereby disconnecting the circuit and preventing electrical shock or fire. The first point of disconnect, which is typically the main panel, is where the service enters the building. This is where the utility company's transformer connects to the building's electrical system. Therefore, it is the ideal location to establish the main grounding electrode system. This system typically consists of a grounding electrode conductor connected to a ground rod, a metallic water pipe, or a concrete encased electrode, often referred to as a UFO ground. The purpose of this grounding electrode system is to provide a connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for fault current to return to the source. Now, let's consider why grounding the neutral at the CT can, which is often located upstream of the main panel, is not recommended. If the neutral is grounded at both the CT can and the main panel, a parallel path for neutral current is created. This parallel path can lead to several problems. Firstly, it can result in circulating currents in the grounding system, which can cause electromagnetic interference and potentially damage sensitive electronic equipment. Secondly, it can create a shock hazard, as the grounding conductors may carry significant current under normal operating conditions. Thirdly, it can interfere with the proper operation of ground fault circuit interrupters, GFCIs, which are designed to protect people from electrical shock. GFCIs work by monitoring the current balance between the hot and neutral conductors. If there is an imbalance, which indicates that current is leaking to ground, the GFCI will trip and disconnect the circuit. However, if there is a parallel path for neutral current, the GFCI may not detect the imbalance and may not trip, leaving the person vulnerable to electrical shock. Floating the neutral as subpanel simply means that the neutral conductor is isolated from the subpanel enclosure and the grounding electrode system at that location. The neutral conductor is still connected to the neutral busbar in the subpanel, but the busbar is not bonded to the enclosure. This configuration prevents the flow of neutral current through the grounding system and eliminates the potential for ground loops. It is important to note that even when the neutral is floated at subpanels, the equipment grounding conductors must still be properly connected. Equipment grounding conductors provide a low impedance path for fault current to return to the source and are essential for electrical safety. They are connected to the metal enclosures of electrical equipment and appliances and are bonded to the grounding electrode system at the main panel. In summary, the best practice is to ground the neutral at the first point of disconnect, which is typically the main panel, and float the neutral at any downstream subpanels. This configuration provides the best protection against electrical hazards and ensures proper electrical system function. Now let's talk about the NEC, National Electrical Code, requirements related to grounding and bonding. The NEC provides specific guidelines for grounding and bonding electrical systems to ensure safety and minimize electrical hazards. Article 250.24 covers the grounding of service-supplied alternating current systems. It requires that the neutral conductor, also known as the grounded conductor, be connected to a grounding electrode system at the service equipment. The grounding electrode system must comply with Article 250.50, which specifies the types of grounding electrodes that are permitted, such as ground rods, metal water pipes, and concrete encased electrodes. Section 250.24, paragraph 8 requires that the connection to the grounding electrode be made at an accessible location, such as the main panel. This allows for inspection and testing of the grounding connection. The size of the grounding electrode conductor is determined by Table 250.66, which is based on the size of the service entrance conductors. The NEC also addresses the bonding of metal enclosures and equipment to the grounding system. Bonding ensures that all metal parts are at the same electrical potential, which minimizes the risk of electrical shock. Section 250.92 requires that metal enclosures containing service conductors be bonded together into the grounding electrode system. This bonding is typically accomplished using bonding jumpers, which are conductors that connect the metal parts together. For subpanels, the NEC requires that the neutral conductor be isolated from the subpanel enclosure, as we discussed earlier. This requirement is outlined in Section 250.32, which states that the neutral conductor shall not be connected to the equipment grounding conductor at separately derived systems. Separately derived systems include generators and transformers, as well as subpanels that are fed from a separate source. The equipment grounding conductors at subpanels must be connected to the grounding electrode system at the main panel. This connection is typically accomplished using a separate equipment grounding conductor that runs with the circuit conductors. The size of the equipment grounding conductor is determined by Table 250.122, which is based on the size of the overcurrent protection device protecting the circuit. It is important to note that the NEC is a minimum standard and that local codes may have additional requirements. Therefore, it is always best to consult with a qualified electrician or electrical inspector to ensure that your electrical system complies with all applicable codes. Now, let's discuss some common mistakes that people make when grounding electrical systems. One common mistake is to use undersized grounding conductors. The size of the grounding conductors must be adequate to carry the fault current without overheating. Table 250.66 and Table 250.122 provide guidance on the proper size of grounding conductors. Another common mistake is to use improper grounding electrodes. The grounding electrode system must comply with Article 250.50, which specifies the types of grounding electrodes that are permitted. Using a grounding electrode that is not listed in Article 250.50 can compromise the effectiveness of the grounding system. A third common mistake is to fail to properly bond metal enclosures and equipment. Bonding ensures that all metal parts are at the same electrical potential, which minimizes the risk of electrical shock. All metal enclosures and equipment must be bonded together into the grounding electrode system. A fourth common mistake is to ground the neutral at multiple locations. Grounding the neutral at multiple locations can create ground loops, which can cause problems with the operation of the electrical system. The neutral should only be grounded at the first point of disconnect. Let's talk about the practical implications of improper grounding. Improper grounding can have serious consequences, including electrical shock, fire, and equipment damage. Electrical shock can occur when a person comes into contact with a live wire and a grounded surface. If the grounding system is not properly installed, the person may become part of the fault current path, which can result in serious injury or death. Fire can occur when a fault current flows through a high resistance path, such as a loose connection or damaged wire. The resistance can cause the wire to overheat and ignite nearby combustible materials. Equipment damage can occur when a fault current flows through sensitive electronic equipment. The fault current can damage the components of the equipment and render it inoperable. Therefore, it is essential to ensure that your electrical system is properly grounded and bonded. This will help to protect you, your family, and your property from electrical hazards. When dealing with electrical systems, always prioritize safety. If you are not comfortable working with electricity, it is best to hire a qualified electrician. Electricity can be dangerous, and it is important to take all necessary precautions to avoid electrical shock or fire. Before working on any electrical circuit, always turn off the power at the breaker panel. Use a voltage tester to verify that the circuit is energized before touching any wires. Wear appropriate personal protective equipment, such as rubber gloves and safety glasses. Be aware of your surroundings and avoid contact with grounded surfaces. If you are unsure about any aspect of the electrical work, consult with a qualified electrician. They can provide guidance and assistance to ensure that the work is done safely and correctly. Remember, electrical safety is everyone's responsibility. By following these guidelines, you can help to prevent electrical accidents and protect yourself and others from harm. Let's briefly discuss surge protection. While proper grounding is essential for safety, it doesn't protect against voltage surges caused by lightning or utility switching. Surge protective devices, or SPDs, are designed to divert these surges to ground, protecting sensitive electronic equipment. SPD should be installed at the main panel and possibly at subpanels for enhanced protection. In conclusion, grounding and bonding are critical aspects of electrical safety. Ground the neutral at the first point of disconnect, typically the main panel, float the neutral at subpanels, and properly bond all metal enclosures and equipment. Consult the NEC and local codes for specific requirements, and always prioritize safety when working with electricity. Understanding these concepts is crucial for anyone working with electrical systems, from homeowners to electricians.